In this video, I'm going to talk about the birth and death process, which in the queuing theory will help us to look at the state of a queuing system. So let's start. When I mention the state of a queuing system, it means that the number of people present in the system at a particular time, t. So this birth and death process will help us to analyze how many number of people are present in our queuing system. So let's denote Pijt equals the probability of j people present in the system at time t, given that I people present at time 0. If you recall, in the Markov chain, if you learned about Markov chain or later if you're learning Markov chain, you will see that we have a steady state probability in Markov chain. It is denoted by pi j, and it's exactly the same thing here. So pi j is when we have a very large t, so we can also say that the system has reached the steady state because so many times have passed since the time 0 or the beginning of the system. So when we have a very large t, we can say that this probability has been steady. It doesn't matter how many people at the beginning of time 0. So in other words, we are going to ignore I. We can say that the probability of having j people present in the system equals pi j. Okay, so pi j is the probability of having j people in the system. We can also say this is the fraction of time that we have j people in the system. The main point here is that in the steady state, we can ignore the I that we have here. In other words, as I said before, it doesn't matter how many people exist at the beginning of time 0. After the steady state, we can say the probability that we have j people equals pi j, not pi ij, but only pi j. And that is the steady state probability of having j people in the system. Now let's take a look at the laws of motion that govern the birth and death process. The birth and death process is a continuous time stochastic process, and then the state of the system at any given time is a non-negative integer. Because remember, we are talking about the number of customers present in the system, so obviously it cannot be negative and it is integer. So the first law says that with this probability, we will have a birth occurs, and this birth will increase the state of the system from j to j plus 1. And this variable lambda j is called the birth rate in the state j. And then we can interpret this birth simply as an arrival. So a customer arrives such that the state of the system increases from j people to j plus 1. The second law says that with this probability, we have a death occurs, and then it will reduce the system state by 1 from j to j minus 1. Mu j is the death rate for the state j, and then although the name is quite scary, the death, in the queuing theory it says death is simply meaning the service completion. Somebody completes the service in the queuing system, so he or she gets out from the system. That's why the state of the system is reduced from j to j minus 1. And then there's a note here saying that mu 0 equals 0 must hold because when we have 0 people in the system, so nobody in the system already, no death can occur because we do not have any customer. So there will be no customer completes the service. That's why mu 0 equal 0. And finally, the births and deaths that are independent of each other means that the arrivals of the customers does not affect the service completion of the customers that are already in the system, and also vice versa. So there are two additional notes here. The first saying that if either inter-arrival time or the service time are not exponential, then the birth and death model is not appropriate. The second thing is that we've seen this again and again. It's saying that at this small time interval, the probability of having more than one event, either birth or death, is practically zero. So at a particular point of time in a small time interval, only one event can happen. To describe the birth and death process in a queuing system, we're going to draw something that is called a rate diagram. So here's the rate diagram for a MM1 system. We see here that first the number inside the circles, they are the states of the system. So here it means 0 customers in the system, 1 customer in the system, 2 customers in the system, j minus 1, j plus 1, and then it can go on forever in the system because this system has the capacity of infinity. So customers can keep coming and queuing up in this system. Now, every time the state of the system increases, it means that a customer arrives. So this is called the birth process. So these arrows, they represent a birth because a customer arrives and then it increases the number of customers in the system. Now, the other arrows decreases the state of the system. Let's say here from 1 to 0, 2 to 1, and so on. These are the deaths in the system. So, okay, so these deaths represent the service completion. Somebody finished with his or her service, and then so he or she left the system. That's why the number of customers in the system decreases from, let's say, 2 to 1, 1 to 0, and so on. And then you may notice here that the rate of the birth is lambda, and the rate of the death is mu. And it's all the same for this MM1 system. It may be different for the other system. So let's take a look at an example for the other system. Here we have MM3, so which means that now we have 3 parallel servers in the system. Okay, so 3 parallel servers in the systems, 3 parallel servers in the system, and then we see that this birth and death process can, the state of the system can keep going because again, the capacity of the system is infinity. Now let us notice first for the birth process or the arrival, the rate stays the same, always lambda. Again, it happens only in this system. It may be different in the other system. But here for the system, the lambda stays the same. There equals 4. But now things get a little bit more interesting if you look at the service rate. So when you only have one customer, obviously you only need one server to handle that customer. So the rate is 5 because here it is given that mu is 5. However, when we have 2 customers, we need 2 customers to work. So the death rate becomes 2 times 5 equals 10 because now there are 2 servers are working. So in the system, the rate of completion becomes 2 times 5, it becomes 10. When we have 3 customers in the system, all 3 servers that we have must be working. So now this system, when they have 3 customers, the rate of doing the completion of the service becomes 15 because we have 3 customers, we have 3 servers working. Each server can work with the rate of 5 customers per hour, let's say. So 3 of them can generate the rate of 15 customers per hour. Now, when we have 4 customers, the rate is still 15. When we have 5 customers, the rate is still 15 also because we only have 3 servers. So whether we have 3 customers, 4 customers, 5 customers, 6, 7, 8, whatever number of customers greater than 3, we will only have 3 customers. So we will only have 3 servers working. That's why in this system, the mu will become 15 at most once we have 3 customers, 4 customers, and 5 customers. Now we're going to use the birth and death process and also the rate diagram to derive the steady state probabilities. Remember that the steady state probabilities, pi j, means the probability that we are having j customers in our system. When we're talking about the steady state condition, we have this thing here. The rate at which transition occur into any state I must equal to the rate at which transition occur out of state I. So in simpler words, I would say that anything comes into a state I must equal to anything goes out from that state I. Let's take a look at this rate diagram from the MM1 example, and let's observe the state J. The state J over here. So from state J, we see that arrow comes out from that circle J, and then we see that this arrow here comes out with lambda. So because it originates from J, we name this lambda J. And then another arrow is over here. It is mu J because it originates from J. So these are the things that comes out from J. We multiply that by pi j, which is the probability that we are at this state J. Let's do the same thing for the things that come into state J. So the first arrow is this coming into J. So we name it lambda J minus 1 because it originates from this circle here. Another arrow coming into J is this arrow. We name it mu J plus 1 because it originates from this state J plus 1. So we will have lambda J minus 1 here times pi J minus 1 and then mu J plus 1 times pi J plus 1. So the pi's follows the origin of the arrows. So that shows the flow balance equation for state J. And for the state 0, it's a bit special. We are going to see here that for the state 0, what comes out from this state is lambda 0. We multiply it with pi 0. What comes into the system is mu 1 times pi 1. So these are the flow balance equation for all states, both the state 1, 2, and so on, and this is for state j equals 0. Now we have seen these two equations from the previous slide, but we are going to working on these equations a little bit more, such that we will have a nice formula saying that pi j equals this and pi 0 equals that. Okay, so plug in the j's. So we have several examples here. J equals 0, j equals 1, and so on. And then from the first equation, when we solve this equation for pi 1, we have pi 1 equals this, pi 0 lambda 0 over mu 1. And then we plug in this definition of pi 1 here to the second equation. So we'll replace that pi 1 with what we've got there. Okay, so we replace pi 1 with that. And then we solve this equation for pi 2. And then we notice that pi 2 looks like this. So based on this, next we are going to see that we are going to have kind of a pattern. We have obtained the formula for pi j in the previous slide, and here it is. Now we're going to derive the pi 0 here. So we notice that because these are talking about probabilities, the sum of all probabilities of all possible events must equal 1. In our case, the sum of all pi starting from pi 0, no customer in the system, pi 1, pi 2 up to pi infinity must equal 1. So from there, combining this thing here with this pi j, we will have this equation. So they simply say that if we open the brackets, it say that pi 0 plus summation from j equals 1 to infinity, pi 0 cj, they must all equals to 1. Okay, so this is the pi 0 itself, and this is the sum of all pi j's. And then from here, we can move this thing here to the other side, and then we obtain this formula for pi 0. So now everything is complete. We have used the birth and death process to derive the probability of j people exist in our queuing system, and then this is the probability of no people in our queuing system. And remember, Cj is this. Once we have all the values for the lambdas and the mu's, we can calculate all these steady state probabilities.